Until now, we've worked with groups, and a group consists of a set and one operation. For example, the set of the integers z is a group under addition, so we would always work with one operation at a time. But we know that z has two operations, addition and multiplication. Not only can we add integers, we can also multiply integers. And the same thing can be said about the set of real numbers R or Z12, the set Z12. In both of those, we can add and multiply. And so we'll take this new perspective where we'll start considering both of those operations at the same time. We make the following observation. There are various properties of addition and multiplication that are common to the integers z, the real numbers r, and z12. For example, in all three sets, we have a plus b equals b plus a, so addition is commutative in all three of those sets. So, as our first task, please pause the video and see if you can name other properties of addition and multiplication that are common to those three sets. Here are the properties of addition and multiplication that are satisfied in z and in the real numbers r and in z12. And let's take them one operation at a time, starting with addition. First, z is closed under addition. Next, addition of integers is associative. In other words, we can move parentheses around and regroup elements in the sum without affecting the value of the sum. Then we have the additive identity element 0, such that 0 plus a equals a and a plus 0 equals a for all integers a. Then we have the existence of additive inverses. For each a and z, there exists negative a and z, such that when you add them together, you get 0. Then we have commutativity of addition that we discussed earlier. In other words, a plus b equals b plus a for all integers a and b. Now, if these look familiar, it's because 1 through 4 are the group properties, and therefore properties 1 through 5 say that z, as well as the reals r and z12, each of those is a commutative group under addition, and commutativity comes from property number 5. Now let's go through the properties of multiplication, and these will mirror the properties of addition. So let's start with closure. Z is closed under multiplication. And we also have associativity for multiplication, so we can regroup and move parentheses around when we're multiplying 3 or more elements. We also have the multiplicative identity element, namely 1. So there exists an integer 1 such that 1 times a is a, and a times 1 is a for all integers a. Now, not every integer has a multiplicative inverse. For instance, the integer 3 doesn't have a multiplicative inverse because 1/3 is not an integer. Now, what about commutativity for multiplication? While it is true that a times b equals b times a for all integers a and b, and the same holds in the reals r and in z12, we are intentionally leaving out that property on this list, and we'll explain why later on. And last but not least, we have the distributive law. So a times parentheses b plus c is equal to a times b plus a times c, and similarly for parentheses b plus c times a. And this is the only property that connects both addition and multiplication. So it's a very special one in that regard. Now, because the set of integers z satisfies these 9 properties, we say that z is a ring. And similarly, the set of reals R is also a ring, and the set Z12 is a ring as well. So here's a generalization. A set R is called a ring if it has 2 operations, typically denoted as addition and multiplication, satisfying properties 1 through 9 that we saw in the previous slide. Now that list of ring properties is fairly long, so what I would encourage you is not try to memorize properties 1 through 9, but think about examples, in particular the ring of integers. That is a classic example of a ring, and so what I would recommend is to think about the properties of addition and multiplication that are satisfied by the set of integers z. Now, here are some features that are common to all rings. The first one we've already talked about. Every ring is a commutative group under addition, and that comes from properties 1 through 5. In other words, a ring has 2 operations, but if you focus on just the addition operation, then we can view any ring as a commutative group under addition. However, a ring is never a group under multiplication because the 0 element, the additive identity element, does not have a multiplicative inverse. Here's another feature. By definition, a ring must be commutative under addition. However, a ring does not need to be commutative under multiplication. And in fact, in today's classwork, you'll see examples of rings that are not commutative under multiplication. Now, a ring has 2 operations, and each of those operations has an identity element. So we'll use 0 to denote the additive identity and 1 to denote the multiplicative identity. Here's another notation. Given a ring element A, we will use negative A to denote its additive inverse. Now that always exists. That's guaranteed by the ring properties. And we'll use A to the minus 1 to denote its multiplicative inverse. And that only sometimes exists, but not always. For example, if we consider the element 3 in the ring of integers, then certainly negative 3 exists in Z. However, the multiplicative inverse of 3, sometimes known as 1/3, does not exist in Z. And so once again, additive inverses always exist. Multiplicative inverses only sometimes exist. We'll introduce a couple of new terminologies, but let's first look at some examples. In the ring Z10, we see that 3 times 7 is equal to 1, the multiplicative identity. And therefore, we say that 3 and 7 are units. We also have in Z10 that 5 times 2 is equal to 0, the additive identity. And therefore, we say that 5 and 2 are 0 divisors. So here are the generalizations, starting with unit. So we'll let R be a ring, and an element U in R is said to be a unit if it has a multiplicative inverse in R. And that multiplicative inverse is denoted as U inverse, U to the minus 1. So for example, here we say that 7 is the multiplicative inverse of 3, and we would write that as 3 to the minus 1 is equal to 7. And likewise, 3 is the multiplicative inverse of 7, so we would write 7 to the minus 1 is equal to 3. And so that's a familiar concept of multiplicative inverse, and we're just introducing a new terminology, namely a unit. So an element, a ring element, is called a unit if it has a multiplicative inverse in R. And here is a zero divisor. A non-zero element A in ring R is said to be a zero divisor if there exists a non-zero element B in R such that A times B is 0. So for example, 5 is a zero divisor because 5 is a non-zero element in Z10, and there exists another non-zero element in Z10, namely 2, such that 5 times 2 is 0. So a pair of non-zero elements multiply together to be 0, then those non-zero elements are called zero divisors. So in this particular example, 2 would also be a zero divisor in Z10. Now here are some remarks about units and zero divisors. In any ring, the multiplicative identity element 1 is a unit because it's a self-inverse under multiplication, namely 1 times 1 equals 1. Moreover, 0, the additive identity 0, is neither a unit nor a zero divisor. We know it's not a unit. 0 doesn't have a multiplicative inverse. And by definition, a zero divisor must be non-zero. So the 0 element does not qualify as a zero divisor. So 0 is neither a unit nor a zero divisor, and that's true in any ring. Now please pause the video and work on day 26 classwork, and afterwards we'll review some of the problems and concepts. In today's classwork, we considered several rings, in particular Z12, Z7, Z, and the real numbers R, and we classified their non-zero elements as either a unit, zero divisor, neither, or both. So let's start with the first row, units. What are the units of Z12 and Z7? So here they are. The units of Z12 are the elements 1, 5, 7, and 11. Those are the elements of Z12 with multiplicative inverses. And in Z7, they're 1 through 6, all of them except 0. Now notice the notation U12 and U7. Those were precisely the set of elements in Z12 with multiplicative inverses, the set of elements in Z7 with multiplicative inverses. So now we know why those sets were called U12 and U7, because those were the set of units inside Z12 and Z7. Now what about the integers Z? Well, most integers don't have multiplicative inverses. The two that do are 1 and -1. 1 times 1 is 1. Negative times -1 is 1 as well. So those are both self-inverses under multiplication. And so those are the only units in Z. Now what about the reals R? Well, with the real numbers, almost all of them except 0 are units. And in fact, we had a notation for that set. Recall that R star refers to the set of elements in R that have multiplicative inverses, and those happen to be all non-zero real numbers. Now on to zero divisors, starting with Z12. In Z12, here are the zero divisors. Note that they're all non-zero, and we have 2 times 6 is 0 in Z12, 3 times 4 is 0 in Z12, 8 times 9, 72 mod 12 is 0, so those multiply to be 0, and 10 pairs with 6. 6 times 10 is equal to 0 mod 12. So those are the zero divisors in Z12. And what about Z7? Is there a pair of elements A and B in Z7, both non-zero, that multiply together to be 0? The answer is no. You know, zero divisors are kind of strange elements, and there are no such elements in Z12, and likewise, no zero divisors in Z, nor in the reals R. Now, what about neither? We know that in any ring, 0 is neither a unit or a zero divisor. But how about the non-zero elements? Well, starting with Z12, we see that all the non-zero elements, namely 1 through 11, show up as either a unit or a zero divisor. So there is no neither element besides 0 in Z12. Likewise, in Z7, all the non-zero elements already show up as units. So we don't have any neither here, except for 0, of course. And similarly for the reals R, all the non-zero elements already show up as units, and so we don't have any neither element except for 0. What about the integers Z? Well, we know that 1 and -1 are units, and there are no zero divisors in Z. That means all the other integers, all except 1, -1, and 0, are neither a unit or a zero divisor. Now, what about both? In Z12, for instance, is there any element that is both a unit and a zero divisor? And in looking at these two boxes, we don't see any overlap, and therefore the answer is no. There is no element of Z12 that's both a unit and a zero divisor. And the same can be said about Z7, Z, and R. And in fact, this is true for any ring. Given any ring, there is no element in that ring that's both a unit and a zero divisor. And that's the theorem that we will prove in the next slide. And here's the theorem that we're going to prove. A ring element alpha cannot be both a unit and a zero divisor. And we'll proceed by contradiction. So let's assume for contradiction that alpha is both a unit and a zero divisor. So let's take these one at a time. First, what does it mean that alpha is a unit? Well, that means that it has a multiplicative inverse. Therefore, there exists alpha inverse in R such that alpha inverse times alpha is equal to 1. And next, let's decipher what it means for alpha to be a zero divisor. Now that means there exists an element beta in ring R that's not equal to 0 such that alpha times beta is equal to 0. In other words, alpha and beta are non-zero elements that multiply together to be 0. That's what it means for alpha to be a zero divisor. Here we've highlighted beta not equal to 0 in red because that's where we're going to obtain our contradiction. So we'll work with this equation alpha times beta equal to 0. And what we're going to do is essentially cancel this alpha, which leaves us with beta equal to 0, leading to our contradiction. Now, how are we going to cancel this alpha? Well, we're going to multiply both sides of this equation on the left by alpha inverse. And so if we do that, we're going to multiply both sides of this equation on the left by alpha inverse. What do we get? Well, let me just highlight the original equation here. So we have alpha times beta equal to 0, and then we multiply both sides on the left by alpha inverse, and then we use the associative law to regroup this side of the equation. So we're left with alpha inverse times alpha times beta is equal to alpha inverse times 0. Now what happens to this equation? Well, let's take one side at a time. On the left we have alpha inverse times alpha. So that just becomes 1. So this whole expression on the left becomes 1 times beta. What about on the right? Well, we have alpha inverse times 0. And anything times 0 is 0. And therefore, this is what we get. We get on the left-hand side 1 times beta. Once again, this product is just 1. And on the right-hand side, anything times 0 is 0. Now, that's something to be careful about. By definition, 0 is the additive identity. In the ring properties, there's nothing that says how 0 behaves under multiplication. And so in fact, it's a theorem that any element of a ring times 0 is 0. It's a theorem that can be proved from the ring properties. And so please take a look at the chapter 26 reading to see why alpha inverse times 0 is equal to 0, and for that matter, any ring element times 0 is equal to 0. And so we have 1 times beta is equal to 0, but 1 being the multiplicative identity element, 1 times beta is just beta, and so we're left with beta equals to 0, which contradicts beta not equal to 0, which was part of the definition of beta. And because of this contradiction, there is no such element alpha that is both a unit and a 0 divisor. And that's the end of our proof. Now here are a couple of coming attractions for the next lesson. First, in a finite ring, in other words, a ring with finitely many elements such as Z12 or Z7, in a finite ring, a non-zero element alpha cannot be neither a unit nor a 0 divisor. In other words, every non-zero element in a finite ring must be either a unit or a 0 divisor. And that explains the none that occurs in Z12 and Z7. And moreover, Z7 and the reals R are almost multiplicative groups because almost every element of Z7 has a multiplicative inverse except for 0. And likewise, almost every element of R, except for 0, has a multiplicative inverse. And so we say that Z7 and R are almost multiplicative groups. And we'll generalize that idea in the next lesson. But for now, that's the end of this lesson, and I will see you next time.